During the previous lecture, we have formulated the theory behind factor analysis. Now it's time to put this theory to work. We have at our disposal the dataset containing information about 329 communities that we rated on different criteria. The criteria were as follows: the climate, housing prices, quality of healthcare, crime level, quality of public transportation, availability of good education, availability of culture, recreation, and economy. Almost all scales are designed in such a way that the higher level, the higher number on the scores, the better community. The exception is scale number 2 about housing prices, where lower numbers indicate lower housing prices, which is essentially probably better. And crime level, lower crime level also means that the community is more friendly, therefore better. We are performing on this data factor analysis, trying to find smaller number of factors that explain the differences in assessing the quality of community. The idea behind this analysis is that probably there are some fewer factors that influence the way how people rate their community, and we are trying to find these factors. First, let us take a look at our data. Here are histograms for all 9 variables. And as you can see, some of them are skewed towards lower values. For example, this one, maybe this one also. And the numbers are very big because these are sums of scores given by a number of people living in the communities. So there are high numbers. Taking into account the fact that they are skewed, some of them are skewed towards lower values, we apply logarithm with the base 10. And then we look what happens. Now the histograms are more or less symmetric. Yeah, some of them are still skewed, but not that much. So we will be working on this transformed data. Since the scales are different, maybe not that much. This is from 0 to 3, from 0 to 4, again to 4, again to 4. No, okay, maybe the scales are more or less the same, but mean values are different. I suppose it will be good to standardize the data. We do not lose any information. And then correlation becomes the same as covariance and things get easier to interpret. So let us standardize the data. Here we create new data set with standardized variables. And then we find correlation matrix, which is in this case the same as the covariance matrix for the standardized data. We will extract our factors using principal component analysis, which means from the mathematical point of view that we calculate eigenvectors and eigenvalues of the correlation matrix and then analyze the outcome, try to interpret those eigenvectors in terms of some indices that summarize the information contained in the dataset. So here we find eigenvalues and eigenvectors for our correlation matrix. And also we calculate some numbers that will be useful in first selecting the number of components, and then assessing the quality of our model. Since we work with standardized variables, that means that correlation, this covariance or correlation matrix has ones on the diagonal. Therefore, the trace here, this is 9 variables, 9 by 9 matrix. The trace is equal to 9. So the whole variability contained in this data is equal to 1, and we would like to explain as much of this number using our principal components or factors in this situation. Okay, so first let us check how many factors we should select, and we have those 3 criteria at our disposal. The first criterion is choose principal components that are at least that correspond to eigenvalues being at least 1. So here we have the appropriate picture. There are ordered eigenvalues, and there is the threshold 1. So this first criterion shows that we should use 3 components for first, second, and third eigenvalue. Then there is this elbow criterion. We draw the line through the points corresponding to eigenvalues, and we check whether this shape changes. And it changes around eigenvalue number 2, which would suggest that we can use only 2 components. No, because then the decrease is much slower. However, using only 2 components means that we forget about 1 component with quite high eigenvalue. So this is the second possibility, the second rule. And the third rule we can apply is to look at the cumulative variance explained, the percentage of variance explained in the consecutive numbers of components. And when we take 2 components, we explain only half of the variance. Then with 3 components, this will be a little bit above 60%, with fourth component close to 8, and the threshold, the customary threshold is 0.8, so 80% of the whole variability contained in the data. And this means that we will have to use as much as 5 components. That makes the model probably too complicated. So looking at these 3 possibilities, I somehow decided to use the middle one, the middle in a sense of in terms of number of components, which means take 3 components all with eigenvalues greater than 1. This means that this model will not be very good because there is still some variability left to explain. We could do the same for 4 components. But let's start with 3 and check what happens. Here I have calculated this cumulative percentage of variance explained by 3 components and 4 components, and we see that this is 62 and 72%. Okay, so deciding on factors, we calculate the factors. Mathematica gives us normalized eigenvectors. So we can just use the formula that was presented previously, and to have a factor we have not only take the eigenvector but also divide it by the square root of the eigenvalue, because what we have to have are factors which are standardized, so their variance should be 1. And this we achieve by dividing by square root of the eigenvalue. And here you can see that I have multiplied all the eigenvectors that I got from Mathematica by -1. I mean, reversing the arrows in a sense. The signs are here can be chosen at random. No, not at random. It can be chosen freely, let's say, which means that we can adapt our factors to the interpretation. Maybe sometimes multiplying by -1 gets our interpretation easier. And this is the case in this situation. In principle, there is even more freedom. We can rotate those factors. They are not then eigenvectors anymore if they are rotated, but they are again orthogonal, and maybe after rotation the interpretation becomes easier. It turns out in our example that we don't need to rotate our factors because the interpretation comes out naturally. But in the next example, when we will be discussing Varimax method of rotation, this rotation improves matters, so sometimes it is useful. Here I only used multiplying by -1 to improve the interpretation. Okay, so let us then go further. We have our factors. Here I've put the formula for factor number 1. As you can see, it is just a linear combination of initial variables with coefficients that come from our analysis. There are roughly coefficients of eigenvector, normalized eigenvector, then divided by square root of eigenvalue. So here we have coefficients for all our factors. However, from this we cannot judge really about we cannot get any interpretation. What we want is rather the matrix of loadings, which is similar. However, we take, instead of dividing our eigenvectors by the square root of eigenvalues, we multiply by the square root of eigenvalues, and then it gets, what we get are correlations between factors and initial variables. And here we have a table of those correlations. So this is the matrix of loadings. Now let us look at the matrix of loadings and let us try to interpret those loadings somehow. Maybe it will be easier to look at the matrix in this form. This is the same matrix as before. However, with highlighted entries, some of the entries. So let us look at eigenvector number 1, factor, not eigenvector, factor number 1. As we can see, this factor correlates highly with variable number 2, which is housing prices, variable number 3, quality of healthcare, variable number 5, which is quality of public transportation, variable number 6, which is availability of good education, 7, availability of culture, and 8, recreation possibilities. So as you can see, all those traits, all those variables can be summarized as overall urban quality of life. And I would call this factor just like that, urban quality of life, because high values of this factor point towards the city, which is wealthy in terms of housing prices, so people that live there are relatively wealthy, and have good healthcare. It is well organized in terms of public transport, healthcare, and other services, and offers various possibilities of spending free time, so on culture and or on recreation. So I would say that this first factor summarizes all the traits that we would like to see in the community we live in. Let us pass to the second factor. Factor 2 correlates with variable number 3, which is again quality of healthcare. Variable number 4, which is crime level, but we have negative correlation here. So the correlation is opposite from the healthcare. So if on this scale healthcare is high, then the crime level will be low. And there is also correlation with good education, and again negative correlation with the economy or overall economy. So this particular factor I would describe as, I don't know, child-friendly factor. This is, by the way, the name proposed by ChatGPT, but because I couldn't invent the name by myself. Nevertheless, this, in my opinion, this factor is related to the quality of the community from the point of view of family having children. So the higher the score on F2, the better community in this the better community is in this aspect. So high values indicate a city with rather low crime, this negative correlation with crime, with good education, with good healthcare, but not very developed economically, which can have something to do, for example, I don't know, with the quality of air, if it is not polluted, yeah. And some people think that maybe raising children in more relaxed environment, which is usually not associated with economically developed places, is better. So that's my interpretation of this quite high negative correlation with economical development. And finally, there is factor number 3, which strongly correlates with climate, and also not that strongly, but quite strongly and negatively correlates with economy. So this is something that I would call nature factor. So we look if our community is close to nature, or it is rather urban. So higher scores on F3 will indicate that I don't know, the city is in the forest. And the lower score will show that this is industrial city. Yeah. So I suppose even though the factors, some factors correlate with strongly with more than one variable. For example, factor 1 and 2 correlate strongly with variable number 6, which is quality of education, and also with variable number 3, which is quality of healthcare. And usually such a situation that factor correlates strongly with more than one variable makes interpretation difficult. However, in this particular situation, I think that we could find a meaning behind the numbers that we have got here. And the same is with respect to factor F2 and F3. They both correlate strongly and negatively with economy. So this is, since these are situations that usually makes interpretation difficult, I marked them in red. Maybe I should mark this also in red, because I have strong correlations here with two factors. However, this is much, I mean, that this first correlation with this first factor is much higher than that's why I didn't put it in red. But still, there is strong correlation with strong correlation of one variable with two factors. Okay, so this is for the interpretation. So overall, I would say that when we assess our community in which we live in, we take into account the overall organization, if it is thriving, well organized, with easy access to everything that we need. So this will be the F1 factors. Then F1 factor. Then we look whether it is good to have children there, if it is children friendly, if we can raise children in this community, and then we also are interested if it is close to nature or rather industrial. And this model explains, as we mentioned before, 64% of the overall variance of the data, which means it is not very high, but I would say acceptable. There is one more possibility of the factor analysis, which is rotation of factors. I think that in this particular example, this rotation is really not necessary, because we were able to interpret sensibly our factors. But let us just look how things can be changed by rotation. Here we have plots of variables from 1 to 9, how they are positioned on the plane defined by factors. So here we have factor number correlations with factor number 1, correlation with factor number 2, and points refer to initial variables, how they correlate with factors. Usually what we want to obtain is to have those points as close to the axis as possible. For example, here we have more or less ideal situation. Almost all the variables are close to at least one axis. For example, 3, 8, 2, And there is a mistake here because we have label number 2 twice. Let me find it. The label number 1, 2, 3, 4, 5, 6. It should be 7 here. Sorry. 7. Once more. 7. Okay. So almost all variables are close to the second axis. So they have small correlation with the first variable, but with the second variable, with the third variable, but for the first and the 9, no, the first is also close to the axis, but the score is high. So this shows that it is not very much correlated with F2 and strongly correlated with F3. The only problem is the variable number 9, which is negatively and strongly correlated with factor number 2 and factor number 3. However, by rotating in this plane, probably we cannot achieve any more. No, we could maybe a little bit rotate this, put this axis like that, then the other will be orthogonal like that. It may a little bit improve it, but I don't think it's necessary. And again, when we look at this picture, F1, F3 plane, so this is almost ideal. There are no strays. All the points are close to at least one axis, and again there is the label mistake here. Yeah. But now we have label number 7 twice. Is it that true? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this 7 is not the label, it is just a correlation. Okay, sorry, my mistake. So now this picture is correct, with correct labels. So what I did, just for experiment, I applied the rotation in the plane of 2 first components. As you can see, the angle of rotation is 45 degrees, so P divided by 4. And did it improve matters? Maybe a little bit, but still we have this variable strongly correlated, variable number 7, strongly correlated with 2 factors, and the last variable number 9, strongly correlated with 2 factors. I didn't even try to interpret these factors because I think it is not really worth doing. I mean, the initial factors are quite okay. So now let us go through assessing the quality of our model. We calculate commonalities for each variable. So we try to determine what is the percentage of variance of each variable, which is explained by those factors that we chose. So here are those percentages. So this 3-factor model explains roughly 80% of the climate variable. This is the first variable. 52% of the housing prices, and so on and so on. All the percentages are higher than half, which is not that bad, but usually we like them to be around 80%, so it is not perfect. Maybe using 4th factor will improve matters. It will definitely improve matters, but the question is how big the improvement. Then total commonality, this was already calculated in several ways. This is the sum of eigenvalues for our 3 rescaled to the total trace. Yeah, so the percentage of the total trace contained in the first 3 eigenvalues, which is the same as the sum of the first 3 commonalities here. And sorry, not the first 3 commonalities, but the sum of the all commonalities, because these are with respect to initial variables and not the factors, so we have to sum over everything. And this is the number that we have obtained before, and it says that 62% of the total variance is explained by the model. And finally, there is this third criterion of our model, which is essentially looking at correlation matrix of errors, or covariance rather. This is the covariance matrix of errors, not correlation. And what we see, there are diagonal elements highlighted here in pink. Essentially, for good model, this matrix should be diagonal. Of course, in true examples, it is almost never diagonal, and we can see that there are big off diagonal, not very big, but not that small, off diagonal elements here. The problem with the principal component method of extracting factors is that it does not give us any criterion of checking whether these numbers, these off-diagonal numbers, are small enough or not. There is not like there is no test for checking if it is small enough or not. Therefore, what we can do is just look for them and decide for ourselves. So I've marked here in orange those numbers that I think that are not low enough, but okay. Summarizing, the quality of our model is not excellent. We have probably too small fraction of the total variance explained. We have satisfactory percentage of the variance of each variable explained, and we have probably not the matrix of covariance of error is not diagonal enough. We could check what happens if we will add another factor to the game. This will definitely improve matters, but we cannot be sure that the model will be perfect. Yeah. And there is a question of interpretation of this additional factor. We could look let us look at loadings and check whether there are variables that are not represented in any of the factors, and what we can see is that they are not. So all the variables here are correlated quite strongly with at least one factor, so I don't expect this improvement to be significant. Okay, another thing that we can do is to apply rotation. Usually, of course, we do not do it manually. Usually we apply one of the known procedures, that should be O here. And this one of the procedures, the most common, is Varimax rotation procedure that we will discuss during the next lecture. In our example, this rotation is not really necessary, but just for curiosity, I tried to just do something and check whether I can achieve more easy to interpret factors by rotating. Previously, we tried to rotate with respect to first in the plane of first and second component. Here we have a rotation. We check what happens if we rotate in the plane of second and third component, and I can move here the angle and look what happens. Yeah, which is the from 0 to 2 pi. So this is the full rotation. The goal is to obtain as many of variables lying close to axis. So here is probably some of the possibilities, with variable 6 being somewhere astray, and here there will be problem with variable 4. Yeah. Nevertheless, in this particular example, it is not needed. The next example, which is based on the European values study, will be about that and about the systematic procedure, how to do it and how to calculate this rotation. But this will be the subject for the next lecture, and I suppose the next week. This is all for now.